Welcome everyone to this new webinar on control education. This webinar is organized by IFAC TC 9.4 Control Education in cooperation with IFAC TC 7.3 Aerospace. And actually, this year's webinar is also organized in cooperation with the IEEE Technical Committee on Education of the Control System Society, and I thank John Hedengren for his cooperation. And I also thank Paolo Castaldi, who is the chair of IFAC Technical Committee 7.3. It's a great pleasure for me today to introduce Laurent Burlion, who is assistant professor at Rutgers University in New Jersey. And previously, he worked for the French Aerospace Lab in Toulouse. His research interests include nonlinear control design for complex and uncertain systems, particularly within the aerospace domain. And today, he will talk about chasing sloshing as a control educational experience. Thank you very much, Laurent, for being here. And now the stage is yours. I remember that after the presentation, there will be time for questions after that. Okay, thank you again, Laurent. The stage is yours.
So hello, everybody. So let me share my screen. Okay, so thank you very much, Antonio. Thank you very much, Paolo, for the invitation. So it's an honor to give this webinar today about a particular project that I started at Rutgers a few years ago. So this is an experience. This is just a snapshot of an ongoing experience that I'm going to show you today. So it's still in progress, but we still have some quite nice results to show. So let me start. So as Antonio said before joining Rutgers, I was a research scientist at the French Aerospace Lab. So that's where I started looking at problems posed by the industry. And often in aerospace, the most interesting problems, as you know, are directly posed by the industry. So working with Airbus, I was able to work on a auto landing solution for aircraft in case of emergency, especially when we don't know the size of a runway. So it can be a rectangular shape somewhere and we need to perform an emergency landing. So I had the opportunity to learn from this experience and to work with many academic partners. And that's also where I met Jean Mignot at the French Space Agency, and we discussed about the sloshing problem, which is the topic of this webinar. So as most of you, my research aimed at using control and designing controller in order to make sure systems operate properly and in a very large envelope. So my focus is in terms of control, nonlinear systems, uncertainties, state constraints, or input control saturation, because in real life, as you know, we always have some constraints on actuators, but also on some sensors. So at Rutgers, I work on satellite, drones, floating offshore wind turbines as applications. So in 2020, I started my satellite lab. I also have a drone lab. So we started with a student project about a kind of inverted pendulum with 2 reaction wheels. And then step by step, we built what we call a sloshing test bench, which is going to be explained a bit further. So my idea is to engage the students through research and through some applications. So there is a kind of circular flow between application, research, and education. And also the project I'm going to discuss today is not a project that we teach in class. It is outside of the classroom. And this is a project that students can, they will not get any grade, any credits for working on it. But as you will see, they are going to get a lot of experience. So this is an overview of the presentation. So today I'm going to discuss about the sloshing problem, our recent contributions with different collaborators in terms of sloshing control. And then I will speak about the education part. So SpySat is the name of our nanosatellite project. So I will discuss about the mission, the design, and the feasibility. So This mission is particularly control-oriented because the aim of the scientific payload is really to work on control solutions and to test them. Contrary to many nanosatellites, which have a scientific payload, basically most of the time an instrument. So particularity of this mission is that we really designed this mission to test some control solutions. And then I will speak about the next steps and conclusions, and I will try to open the topic and our benchmark to the control community. So the sloshing problem is, so by sloshing, we mean the movement of liquid inside the container. So as you can see on the left, there is a video, there is a truck, and the truck brakes at 0.5 G. And as you can see, there is no baffle inside the container. The liquid is moving a lot when you decelerate, and this can create some internal forces and torque acting on the truck. So sloshing affects many systems. It can be a boat with many containers. It can be the wing of an aircraft, or it can be also a rocket, like for example, the SpaceX rocket. And of course, there is a big difference between liquid behavior in 0G, so in space, and in 1G on Earth. But even at higher G, so at 1G, the sloshing problem can be of interest. Oftentimes, sloshing is mitigated in 1G using some buffers. So basically, we are going to separate and to split the liquid into many sections so that it doesn't really disturb the system. But in 0G, so in space, mass is very important. So we want to reduce as much as possible the buffers that we are going to use. So that's why we may be interested even more in 0G in active control and sloshing mitigation. So sloshing is an old problem. So it started in the 1950s. The Apollo mission was about to fail because of a sloshing problem. In 1996, there was also a loss of mission, a near loss of mission for the near-Earth asteroid rendezvous caused by fuel slosh. More recently, in 2007, SpaceX Falcon 1 got some upper stage control oscillation, which were caused by fuel slosh. What are the main factors when we speak about sloshing? Of course, the tank fill ratio is important. If your tank is completely filled, the liquid will not produce a lot of sloshing, will barely move. And of course, if your tank is empty, the liquid will not do anything, right? Because the tank is empty. So usually sloshing mostly affect your system when the tank is filled between 40 and 60%. So of course, the other factors are the acceleration of your system containing the container with the liquid, the properties of your propellant, the geometry, the buffers, if you have some buffers or not inside your tank, position of your tank on your autonomous system, whether it's a satellite or a rocket, and of course the angular velocity and acceleration. So as you can see on the right, we see Thomas Pesquet on board the ISS. And as you can see, the behavior of liquid is really, really different in 0G than on Earth. So viscosity becomes very important compared to gravity. So this problem is old, as I said, but there is still a lot of interest. In 2022, some of you may have attended what we call the Slosh Chamber Seminar Series, organized by ESA and NASA and ONERA and CNES. So there were a few seminars about sloshing given by the NASA, Airbus, CNES, Ariane Group. So as you can see, looking at the title, there are still many people working on sloshing mitigation on control. Also, I started working on this problem because of what we call the fluidics experiment, which was performed on board the ISS, notably by Thomas Pesquet, from 2016 to 2019. And my colleagues at ONERA are already working on the next phase and the next fluidics, I think it's fluidics L experiment in the years to come. Artemis is a very important mission, as you know, and one module, Orion, performed some slosh test in the summer of 2022 when before we send again some humans on the moon. James Webb Telescope also launched in 2022 as observed in the documentation, propellant slosh is taking 20 minutes to dampen in some cases. So which is long, right? If you want to maneuver, it takes 20 minutes just to have the liquid settled. So in terms of control, the basic, if you take just consider 1 degree of freedom, 1 axis of rotation of a satellite rotating around this axis. So basically your state will be if you look at the attitude control problem, will be the angular position around this axis and the angular velocity. So we all know the blue blocks, right? You have guidance, which generates the desired profile for the angular velocity, angular position, etc. You have the controller and some actuators, satellite rigid body model, and that's how we perform an attitude maneuver. So in terms of sloshing, the fact that you have a container with some liquid, you have this internal additional block, which produce for the attitude control an internal torque, gamma S, that we want to reject. Right? So in the last few years, I work on several topics in terms of sloshing. First of all, I work with my colleague from the French Aerospace Lab, ONERA. We advise a PhD, Anthony Bourdelle, who defended his PhD in 2021. So Anthony Bourdelle had access to some data from the fluidics experiments. So based on this data, we publish a model, LPV model. Also, we work also on LTV model. So Anthony mainly work on observer design in order to estimate the sloshing disturbance torque. And also he work on some anti-wind-up and reference governor design in addition to that. More recently, another student, Guido Magnani, again advised by ONERA, visited me at Rutgers, but during his PhD at Toulouse, he worked on reference governor again and adaptive control combined with reference governor. So I'm going to speak a little bit about reference governor in the next slide. So reference governor is a particular constraint control method. Manav Jadeja at Rutgers was of my master science students, and he worked on a closed loop CFD simulator using OpenFOAM. And then he joined SpaceX last year. Mike Fogel is my PhD student, still working on this topic. So for his master thesis, he worked on machine learning and estimation using neural network on the sloshing torque of the sloshing torque. He is involved in our CubeSat mission and he leads the payload development. Then I had also another visitor from IIT Roorkee, Ashish Kumar, funded by the IEEE CSS. And he worked last summer on deep reinforcement learning in order to mitigate sloshing. So we are very interested in safety. We are very interested in making sure that the sloshing torque is not going to make the satellite become crazy, right? So we want to make sure that after a maneuver, even if the maneuver is performed very quickly, the liquid will not disturb too much the system. So that's why we work on reference governor, which is a particular add-on control method that we add in addition to an existing controller. So let's say, for example, a PID controller. So the governor is added to the controller in order to make sure that some constraints, safety constraints, actuator constraints, are not going to be violated. So you can see the reference governor as a particular, maybe simpler MPC method, right, for people working on model predictive control. But contrary to model predictive control, there is already a pre-stabilizer or a nominal controller. So there are also some interesting properties. For example, using reference governor, we can guarantee recursive feasibility, etc. So we can compute the O infinity set for at least for linear systems with linear constraints. So there are still a few challenges when your system is nonlinear or when you have some uncertain parameters. So we also work on these particular challenges in the last few years. So one recent result that is going to be tested on our satellite mission is what we call adaptive reference governor. So basically, we have in our nominal controller the addition of a nominal controller with a MRAC, so model reference adaptive control, and we redesign the reference governor to work with this particular time varying or nonlinear controller, which is a combination of a PD controller and a MRAC, right? So we have a couple of papers about that, and one of them was submitted to NIFAC journal recently. So in terms of education now, so I'm going to introduce this SPICESAT mission. So this SPICESAT mission is a project that is funded by the Air Force. So the aim is to develop the first cube satellite at Rutgers, so our first cube satellite. And the aim is to apply some advanced control methods to this sloshing control problem. So this project is mostly performed by some undergraduate students. Okay, it is led by the student and it is implemented by a student club which is called STAR. So SPICESAT is a sloshing platform for in-orbit control experimentation. So this project is funded by the Air Force. And in 2 years, so we already participated to the phase 1 the last 2 years, and we are going to do it again. And the aim, of course, is to be selected and to launch a CUBE satellite. So this project is unique. It is outside of the classical classroom, and it is a partnership between my lab, Burlion Research Group, and my graduate students, and a student club, mostly based on undergraduate students. And some of them didn't know anything about control before starting this project. So the undergrads are, of course, very proud of the name SPICESAT and their logo, which is very spicy, as you can see. So here is the mission statement. The aim is to study sloshing in zero gravity and implement novel active control laws on a real satellite. So the objective is to investigate and measure fluid sloshing on a CUBE satellite in order to validate some equivalent mechanical models or even maybe create more representative ones. So often people use mass springs or pendulums to model sloshings. But so one of my former students, Anthony, directly work on LPV or LTV models, right, based on the fluidics experiments. So the objective of the mission is to test and develop some active controller to mitigate, so to reduce the fuel sloshing on the CubeSat. So here is the first design on which the student worked this last 2 years. So this is a 6-unit nano satellite, and the tank, so which is fundamental for our mission, and the tank where we will have the liquid, basically represent 2 units. Here we have the ADCS, so that's where you have the reaction wheels. We have the transceiver to communicate with the ground. We have the power also, electrical power, and the camera. So the camera will look at the liquid, and we are going to record these images and send them to our station on Earth. So the tank will be partly filled, like 50% filled of liquid. So we are going to measure sloshing, and we are also going to control sloshing. So to measure sloshing, we are going to fuse different types of information. The classical one is based on the gyroscopes. This is what we call motion sensing suite. So it's classical. That's what we have on most of the satellite, of course, gyroscopes, accelerometers. Then we are going to record sloshing, so using a camera. And we are also going to use some pressure sensors that we are going to put inside the tank. So based on the fusion of this information, we are going to work on system identification and try to get a model of the system. So our mission is based on a few experiments and four controllers. So first of all, we are going to use a baseline controller. So that's that's a controller that is directly provided by Blue Canyon Technology when we buy their ADCS and reaction wheels inside. So we are going to excite and observe what's going on, right? So we are going to make some maneuver at very high angular velocities and observe, measure. So all this experiment A will generate 160 maneuvers and the flight data associated to these maneuvers. Then we are going to test an adaptive controller, which is a little bit more advanced than the original one. Again, we are going to excite, observe, but also maybe mitigate sloshing, try to reduce sloshing. And we are going to collect 26 experiments. Then we are going to test a machine learning controller. So basically a controller which uses an estimation of the sloshing torque using neural network. And the last experiment is more challenging. We are going to combine everything together. So as you remember, I spoke about reference governor and adaptive reference governor. So the last experiment, we are going to combine machine learning, adaptive control, and reference governor. And we are still working on it. So at the end of the day, we are going to collect a lot of flight data and have it on the ground. And we hope, once we have this data, to share it with the control community. So our minimum success criteria will be at least to collect 80 experiments. But hopefully we will have these 238 experiments total. So each experiment will consist in spinning the satellite and collect some data, and also test some active anti-sloshing control methods. Even before launching the satellite, we must demonstrate that we can launch a satellite and collect some good data, right? So the Air Force is not going to fund us and to fund our launch if we don't prove that this mission is viable. So for that, we had to do a lot of things. One of them is, for example, to use a vacuum chamber to make sure that the tank is not going to leak. Another thing is to work on the pressure sensor that we are going to put inside the tank and make sure again that this pressure sensor will be compatible to the space environment. So as an example, we had to change the pressure sensors because the first models that we use was not compatible at all with the space environment. So now we have a new solution. And we have to make sure that the pressure sensor will fit inside the tank, etc. So there are many sub-problems which are not control problems at all. But there are also some control-related problems. Right? We must show that we are going to measure something. We need to show that even before launching the satellite, we need to show that the sloshing torque will be big enough to be sensed by the sensor. Right? Otherwise, we don't need to launch the satellite because we are not going to collect any good data. So we did some CFD analysis for that. We spin the satellite and collect some CFD data, so computational fluid dynamics using, so we can use different software, but Flow3D is often used by the NASA and many other people working on sloshing. Alternatively, I've got a student who worked on OpenForm and another student who worked on ANSYS. So we perform a lot of numerical experiments to get some data and show that our mission will be interesting enough, right? We are going to measure the sloshing disturbance, the amount of liquid or the ratio of liquid compared to the total mass of the satellite will allow us to measure and sense a disturbance torque. So here it's again an example when we measure the different forces and torque generated by the sloshing. We know the characteristic of the ADCS, we know the acceleration and velocities at which we can rotate the satellite. So by using almost the maximum values given by Blue Canyon technology, we show that we can sense sloshing. Another very important problem, we are going to eject the satellite. So there will be an initial kick. So what we call detumbling, are we sure that our satellite will be able to detumble, that we are not going to lose the satellite after this initial kick? So that was a question raised by the Air Force. But of course, this question makes a lot of sense. So for that, we needed to do some closed-loop computational fluid dynamics simulations to make sure that after some time, right, the satellite is going to stabilize, even if there is some liquid inside. So usually when you launch a new satellite, the tank is completely filled. But for our mission, the amount of liquid will not change, right? This is a CubeSat mission dedicated to sloshing. And so the amount of liquid will not vary. So when at the initial kick, we will have some sloshing compared to a classical satellite, because classical satellite, at the initial kick, the tank is filled completely, right? So in our case, the tank will not be filled completely. So we needed to demonstrate that at the initial kick, and despite the initial kick, after a few orbits, the satellite will be able to have an angular momentum reduced despite the liquid inside, right? So when you do this detumbling, we can only use a magnetor curves, and so they are, in terms of control, they produce a very slow amount of torque compared to reaction wheels. Another thing that another student tested was the communication downlead. We need to make sure that every time we are going to download to send the flight data to the ground, liquid will not disturb the antenna, liquid sloshing. So the student used fluent CFD simulations for that, and show that indeed, despite the small oscillations coming from the liquid, we will be able to send the data to the ground. So of course, this I show you the CubeSat, but there were many iterations in order to get this design. First, we started with a 3-unit nano satellite, but then we had to choose finally a 6-unit in order to have a tank large enough, and so to be able to have a sloshing disturbance big enough. We also constructed different test benches in order to test the control solutions on ground before even launching a satellite. So that's now what I'm going to explain. So at the beginning, we had this initial test bench. So it was a spherical tank. You had the gantry, and you can perform a 1 degree of freedom rotation. We've got the camera looking at the liquid, an IMU, one reaction wheel with the motor, and we designed this first stage bench. And after a few iterations, after 2 more years, we ended up with what we call the flat sat, which looks like our nano satellite. It's a 6-unit flat sat, right, with a tank, which is now cylindrical, so which exactly the tank that we will have. And we have 1 reaction wheel for now, right? So this flat sat is what was shown to the Air Force for the first final selection review in January 2024. And now we are working on a new project in order to be selected again in 2027. So as an example, on this test bench, you can use a PID controller and make a maneuver, so from 0 to 90 degrees, and measure, so you see the controller, the error, etc. So we can test an initial PID, and we can see if the liquid creates a disturbance or not by comparing what's going on when there is no liquid or 20% of liquid. So here on Earth, of course, we can vary the amount of liquid. We are also interested in other test benches, at least for education, even if they are not, they don't all look like the nano satellite. So one of them is the hexapod. And as an example, one student worked on machine learning and vision in order to find the frontier of the liquid at every instant. And now we are going to close the loop based on the value of the image processing output. Some other students work on a 3 degree of freedom test bench with now 3 reaction wheels. And later we are going to add a tank again and test some anti-sloshing solutions. So what are the next steps? In terms of control education, now I want to include, okay, this experience was outside of the classroom. We still have another project, but I want to include more and more of these activities in my own classes. So you can use this problem in order to teach control, of course, and to work on modeling identification for undergrads or graduate students. Of course, I'm interested in getting the student feedback, and I'm going to share a few preliminary responses. In terms of research, so our research community may also be interested in getting the data. So we are working on a closed loop computational fluid dynamics simulator, where we are going to generate all the data of the mission. We are going to open this data to the community, and I'm going to show how in a few minutes. And also we expect to launch the CubeSat, because the day we launch the CubeSat, we not have the CFD data, we have the real data. And again, we plan to share it with the community. So as an example of what we can do now in class for the BS, so bachelor or master level, people can work on equivalent mechanical models. So that's an example of a problem that I gave to a basic control class last semester. So people used this 1 degree of freedom example, where the liquid moves inside a container that we moved with a translation, and we approximate the motion of the liquid by a pendulum, right? So the students had to use Lagrangian mechanics to model the system. They linearized the system, they implemented LQR, LQJ controller, and then they did some simulation analysis, etc. And later on, we plan to implement this method on the hexapod that I showed before, which is here, because with this hexapod, we can isolate the translational degree of freedom. So that's the next step. As a PhD level, then of course we can do more complex things. As an example, Ashish came this summer and worked on deep reinforcement learning on the same problem. So slosh container, 1 degree of freedom, and he used this new adjunct policy in order to mitigate sloshing. Another example that we can again do at the BSMS level, so bachelor or master level, is to use the initial test bench that we have with 1 degree of freedom. Again, we can use equivalent mechanical mechanics model using one pendulum or mass spring system to model the sloshing effect. We can derive a model using Lagrangian, etc., linearize the system, test classical control methods, and apply it on the real test bench. At the master or PhD work, we can also use machine learning and control. So here that was the master thesis of Mike, who is now doing a PhD. So Mike trained a machine learning model based on the past value of the state and the current value of the states, and also the control input. This model approximate and give the sloshing torque to be rejected by the controller. Again, at the bachelor or master level, of course, we can later use a 3 degree of freedom test bench, and again, use an equivalent mechanical model. We have now a master, so it's Tamar Leiser working on the hexapod. So again, she can do equivalent mechanical model. And this time there will be 2 pendulum because we are going to look in 3D, right, at the frontier of the liquid. So we will have 2 cameras, 90 degrees between the 2 cameras. And again, she can try to implement a controller. So this master is ongoing. She's also working on database method, so without any model. And she's using a recursive least square algorithm to get a model in real time, combined with model predictive control. So the important question after I show you all these test benches that can be used in class this time, what about 0G? Because all these test benches, as you know, are tested in 1G, right? So that's because of this question, of course, and of course we are going to launch a satellite for that to get some 0G data, that we are also working on CFD simulator, and especially closed loop CFD simulator. It's quite easy to use this CFD softwares in open loop. It's more challenging to couple them with MATLAB Simulink or Python. for the rigid body system coupled with the software. So that's what we are currently doing. We have coupled Flow3D and Simulink, and we are going to generate all the data of the 238 experiments that we plan to do with the real nanosatellite. We are going to analyze this data, build some models, and share the data with the community. So so the next step is we are going to participate to the VNV workshop organized by NASA, ESA, ESA Supero in Toulouse this summer. So that's where we are going to present the initial result of this closed-loop CFD simulator. I'm also working with the IFAC Journal Control Engineering Practice. So we are going to organize a special issue on benchmark control applications. You are also all invited to participate to a special issue. So the aim is to collect some interesting benchmark for control applications. And so we are going to submit a paper about this sloshing problem, and we are going to provide input-output data of our closed-loop CFD simulator. To finish, I collected the student feedback. So I asked them some general question about the project. Basically, what was their overall satisfaction working on this CubeSat project. Then I wanted to investigate a little bit what they thought about control theory. So working on this project, did they get more involved, and did this project increase their interest in control? And then I also survey our future interest. Do they plan to continue working on control, for example, for a master, because most of them are doing a bachelor, etc. So let's look at the initial survey that I did a few weeks ago. So for now, I got the responses of 15 people, all working on the scientific payload on this CubeSat project. So overall satisfaction with the CubeSat project, 4.8 out of 5, which is the maximum, standard deviation 0.3. So basically all the students were very happy to work on this project. I asked some different questions. What did you find most challenging? So as always, administrative task, buying the different parts of the satellite, which can be tricky, management, time, communication between the students, knowledge gap, learning all these control things, modeling things, interfaces between each subsystem. This is a complex problem, of course. What did you find most rewarding about the project? So students really developed a lot of, so really enjoyed, this group project, the community aspect, the friendship between them, support, the working directly on a project which could have a wide impact, because this project is going to space sooner or later. They work on many things. They work on the actual hardware, so the actual reaction wheel that we are going to have on a real satellite. They get this hands-on experience, exposure to complicated hardware, software problems. They learn by doing. And of course, they got a systems perspective, because to build the nano satellite, of course, we need many skills, and it's not only a control problem, but there are other problems to solve, as I said. So now, maybe for us, most interesting questions are about control, right? Did you know anything about control prior to start the project? So most of them replied no, or just a little, right? So to what extent did working on this project expose you to control theory concept? The mean is 3, so in the middle, because all of them work on the control part. I mean, they work on the tank, they work on the pressure sensors. So it's not surprising to see that only maybe a few of them really get this exposure to control. But I think that most of them had an increase in their interest in learning about control. All of them replied, yes, I would like to learn more now because I work on this project. And all of them replied that, yes, they would be interested in getting a better understanding of control theory, working on that project, even if they work on a different part on the satellite, like let's say the power, communication. They are all interested in better understanding what's going on in terms of control. Would you be interested in taking a class on advanced control method? And majority said yes. Future interest, are you going to work once you graduate? Of course, everybody wants to work. Aerospace industry, all of them replied yes. But these students are not necessarily aerospace students. They come from electrical engineering, aerospace engineering, mechanical engineering, computer science, etc. So it's interesting to see that after working on this project, all of them would like to work in the aerospace industry. As a guidance navigation control engineer, just half of them, which makes sense because their background is not necessarily control. And most of them would like to continue a master or PhD, but as you know, in the US, studies are quite expensive, so money could be a problem for some of them. And as you can see, they could potentially join different type of major, not only aerospace and aerospace control, right? So computer science, electrical, physics, astrophysics. Would you rather take an advanced control class? Most of them reply yes. Some of them said, okay, but I would like to make sure that this will not lower my grades, right? If the class is too difficult, maybe it's not a good choice. But then I asked for some general comments. So the first comment is very interesting, right? This project shaped who I am. It was very fun learning about control. Having an actual project to work on makes control theory a bit more tangible, much more interesting. Control is an interesting topic, affects our lives. Fascinating that just an algorithm can do the work of a piece of mechanical hardware like a baffle, but now it's just an algorithm. And one of them said a very good remark, right? I'd like to understand whether data-driven model could be used in control loop, right? This student never work on control and already ask a good question, right? So conclusion, this journey only started 3 years ago. Now we are at a point where the test benches are almost ready to be used. We have many control algorithms to implement and test before even launching a nano satellite. The closed loop demonstration simulations will make our case even stronger. Of course, to launch a CubeSat, we need to convince the Air Force to fund the launch. And interestingly, many students who apply to this graduate program specialize in GNC. So I show you the survey about 15 students, but I have other students who work on this project also before that, and I will continue to survey the students in the future. So the one that I didn't survey, but some of them went to some graduate schools, and interestingly, I didn't know that, but they specialize, all of them, they specialize in GNC. Also, the people who join the industry after that find some very good jobs at Boeing, GPL, SpaceX, Rocket Lab. So it's quite interesting to work on this type of project for a student, of course. And now I would like to thank you for your attention, and I'm ready to take your questions.
Thank you very much, Laurent, for this very interesting talk. Your project is very inspiring and engaging.
Thank you, Antonio.